Hi everyone, today we are going to talk about our project in particle filter-based localization and continuous CSM mapping on the Fold AV dataset. Here's our agenda for today's topic. The Fold AV dataset is a collection of high-resolution sensor data captured by autonomous vehicles in diverse urban environment, and it includes data from cameras, lidars, and GPS, providing a rich source for information for researchers and developers to work on autonomous vehicle technology. The Fold AV dataset offers opportunities for improvement in the EKF framework and the map inference process. We proposed using a particle filter-based localization method to enhance performance due to the potential EKF limitations. Additionally, we introduced a preliminary mapping algorithms as the foundation of the inferring map.
Our solution consists of a particle filter-based localization algorithm that we did a 3D estimate with 15-dimensional state vector, an online filter for application in real time, and we also did a batch implementation to overcome lossy data that we saw in the online filter. Our continuous counting sensor model mapping algorithm is continuous because it is a higher resolution than discrete, and we don't use it for real-time mapping. And since we don't have the semantic class information, we don't use the semantic continuous counting sensor model for mapping. For particle filter-based localization, we do sequential importance resampling. The filter is initialized with 500 particles with equal weight and the same initial state and mean. And for the particle filter, we do prediction where we use propagation based on 3D linearized kinematics. And correction, we measure states directly, so correction is based on directly generating the likelihood off of measurements.
So for the online implementation of our particle filter, it was pretty lossy in that most of the measurements were not being used. This is because we had like a really high computation time for each run of the particle filter, and this was using 500 particles. But even with 500 particles, you can see like there's a drop in ESS pretty quickly, and you have to note that this is within a 30-second time frame. So we pushed the particle filter, the number of particles up to like 1,500, where we got better results. The ESS didn't drop that as much, but this also required perturbing the outputs of the prediction step because it was getting stuck in local minimas. And so this is not like an ideal solution for a particle filter. Therefore, we went back and re-implemented the EKF using the robot localization package, which gave really good results in terms of what the accuracy was, and we had like a error in the order of millimeters.
So the next portion was implementing the continuous CSM mapping, and this algorithm infers the probability of occupancy for each cell on a map that represents the environment of the car, and the algorithm is shown on the right-hand side, essentially updating these parameters alpha and beta that shows values of where the beam of LiDAR is reflected or passes through the grid cell on the map. So in order to implement this continuous CSM mapping with the dataset that we had, we extracted the LiDAR scan data and ground truth poses from a ROS bag, filtered out LiDAR data, and then converted the 3D points into a 2D map by removing points on a different plane than where the car was, and then aligned the time stamps of the LiDAR scan data and the ground truth pose data to then infer the map.
Okay, so this is a result from our mapping algorithm. So the result generally show the trajectory followed the trajectory shown before, but it's really noisy. Although we filled out the data, it still captured opticals that is not on the path. So turning into a 3D map might be helpful. In conclusion, for mapping, the CSF mapping result is really noisy, and BKI mapping framework might help us to make a semantic labeled dense 3D map. For the localization, there's a trade-off between increasing number of particles and overcome the degeneracy and the computation time. So therefore, we need to reduce the computation time for the correction to turn this to online algorithm. As a future work, the mapping and localization algorithm we did can enable a full online stuff. That's all. Thank you.